Hello, welcome to all of you for the 7th program of e-Shikshana. e-Shikshana is an excellent initiative by VTU Karnataka to reach quality content digitally to all the students. Under this program, every semester, a number of courses in different branches are dealt by experts and is available for all the students. In this course, we will be dealing with transmission and distribution of electric power systems. This course is a 5th semester course for the students of electrical and electronics engineering. We all know that electricity is generated far away from the load centers. The power generated at the generating stations should be made available to the customers. And we have varied customers. At the ground level, we have domestic consumers who require power at a low voltage. We have industries who require power at different voltage levels. Therefore, we need to put in place a system where the power generated at the generating stations is transmitted and distributed to the consumers. So, this is what this course is all about. So, first we will be seeing about the introduction to transmission and distribution concepts. What are the different ways in which we can transmit electric power and how do we distribute it to a number of consumers? Once we know the basics, I need to model the system. Now, what is exactly a model of a system? So, when we model a system in engineering, we are going to build mathematical equations. So, we will be deriving mathematical equations for transmission and distribution of systems and see how it affects the various parameters in the system. And why do we need to model? As I said, to analyze and determine certain parameters. Now, whenever we talk of transport of power or power from a source to a load, we talk of efficiency. How efficiently can we transmit power from the source to the load? So, to calculate this, I need to model the system. And we have different distances. We have lines which are short, maybe around 50 kilometers. And we also have lines, transmission lines, which extend to almost 2000 kilometers. So, how does the model of the system vary as we vary the transmission length of the transmission lines? So, we will be studying about these aspects in modeling. And now, once I have a system in place, I need to know whether the system is reliable. So, what parameters would I use to determine the reliability of the transmission and distribution system? And finally, let's say I as a consumer get electrical power. Am I satisfied with the quality of power I get? Right? So, when I switch on a light bulb, let us say, do I get the light from the bulb which is promised to me? And if I am going to run a motor, does the motor run the way it should run? So, these are all various quality issues, and we will also be seeing about the reliability and quality of power transmission and distribution systems. So, this is Professor Uma Rao. I am a retired professor of electrical engineering. I retired from service from RV College of Engineering, Bengaluru, and I will be dealing with the introduction of the transmission and distribution systems in the first few sessions. So the course is 21 EE 51 in the 5th semester and titled Transmission and Distribution. So I will be starting with module 1. Now what are the learning objectives of this session? So first, we will study the introduction to the power system and what is the structure of electric power system. And we will study different concepts of generation, transmission and distribution. You already know about different ways of generating electric power. So we have thermal generation, we have hydel generation, nuclear, solar, wind, bio and so on. So we will not be dealing with the concepts of generation here. Now what we will be seeing is whether I generate the power at the voltage levels as required by the consumer, or do the generation levels, transmission levels, distribution levels, do they have to be different? So we will be studying all these aspects, and at the end of this session you will be able to answer a number of questions in your mind about these aspects. Now let's see how it all started. So the first electric power system was DC. DC means direct current. So this is a metaphor, or you can say, we say direct current voltage, right? So it looks like a misnomer, but anyway that's how it is struck. So when we say a DC system, we mean a direct current system, but please remember I will be generating voltage. I will be generating voltage using the generators. The current drawn is determined by the load. The current drawn is determined by the load. Okay. So the first electric power system was DC, and it was developed in United States and was established in 1882 at New York City by none other than Thomas Alva Edison. So most of us know Edison as the inventor of the electric bulb, but he did a whole lot of other things too. And we owe our beginnings of power system to Thomas Edison. So by 1882, DC generators were already available, and the DC power was generated using DC generators, and it was being distributed by underground cables. Now, due to the high I squared R loss, that is the conductor loss. So to transmit electric power, you need conductors, and conductors have finite resistance. And when current flows through a resistor, there will be some energy lost as heat. So this we call as the I squared R loss. So you have a very high loss at low voltage. We will see why low voltages cause higher losses soon. And the power that was transmitted was only for a very short distance, the first power system which Edison started. So it fed roughly about 60 customers and hardly around 1.5 kilometers radius, and it supplied power enough to light up around 3000 lamps, but it was a complete power system. Okay? So we had a generator, and it was taken to the loads, and the loads were supplied with electric power. So what was the characteristic of this first system? It was high losses, remember that, and short transmission distance. So you will see that if you read the history of any technology and how it evolved, it is these drawbacks which make us want to improve something more and more. So when the first power system was established, two major drawbacks were observed. One was the high losses, and because of the high losses, the short distance. So obviously, for this technology to evolve on a larger scale, we need to bring down the losses so that I can transmit power over longer distances. At that time, in 1882, The major drawback was that there was no way to step up the DC voltage. How do you step up a DC voltage? You cannot do it, right? So we were limited to transmitting electric power at low voltage DC. Now, if there is one invention which revolutionized the entire concept of electric power industry, it would be the transformer. The transformer was instrumental in rectifying the drawbacks we have observed of high losses and short transmission distances, and I would say again that it revolutionized the entire power industry. So that was the starting point for scaling up electric power generation and transmission. Now, let us look at a very good video of Thomas Edison opening the world's first power plant. This video is placed in YouTube, and I would like to place on record my acknowledgement to YouTube for making it available to the public. So now watch this video and see how the systems have evolved from 1882, the first system of Edison, to modern power systems.
Hello and welcome to HistoryPod. On the 4th of September 1882, Thomas Edison began operating the first permanent commercial electrical power plant in New York City. Edison had created his incandescent light bulb in October 1879 and was quick to realise that he also had to develop a system to generate and distribute the required electricity to consumers. Having successfully installed a number of smaller private systems in both the United States and Britain, Edison bought 2 adjoining commercial buildings on Pearl Street in the area known as the First District in New York to house his commercial power plant. Installing the 6 dynamos and their coal-powered reciprocating steam engines was a significant technical challenge, but one of the most expensive aspects of the venture was the laying of almost 100,000 feet of wiring in specially dug underground conduits. By the time the system was ready to begin operation on the 4th of September 1882, Edison had signed up around 80 customers with a total of 400 light bulbs. The New York Times, one of the first users, described the soft, mellow light in a short article the next day. However, the inauguration of the world's first commercial power plant really didn't receive the media fanfare many might have expected, and the report itself was filed under miscellaneous city news. Edison's customer base eventually increased to almost 500 users within 12 months of the Pearl Street station opening, but it ran at a loss for the first 2 years. The system did, however, generate demand for electrical energy elsewhere, and it kick-started the electrical age. The shortcomings of Edison's direct current soon became apparent, however, as it was prohibitively expensive to provide such power over long distances. Within just a few years, competitors using high-voltage alternating current had begun to dominate the market.
This is Dave, head of marketing at a ketchup company about
The development of electricity was like the rapid development of the automobile, computers, or the internet. Everyone could see that it was useful and amazing, but nobody knew quite how to utilize it or what the standards would be. It could be said that Thomas Edison created the idea of a centrally located power station, The only problem was that the direct current power he was using did not transmit very far.
You could only transmit direct current a few thousand yards from a Edison generating station.
It was quite obvious to George Westinghouse that direct current was never going to be a national model. It's just a local model.
That meant that in order to power a city, he would need power stations every mile or so that were small and practically in their customers' backyards. The development of electricity was like the rapid development of the automobile, computers, or the internet. Everyone could see that it was useful and amazing, but nobody knew quite how to utilize it or what the standards would be. It could be said that Thomas Edison created the idea of a centrally located power station. The only problem was that the direct current power he was using did not transmit very far.
You could only transmit direct current a few thousand yards from a Edison generating station.
It was quite obvious to George Westinghouse that direct current was never going to be a national model. It's just a local model.
That meant that in order to power a city, he would need power stations every mile or so that were small and practically in their customers' backyards. These facts did not stop Edison from promoting DC power with the theatrics and flair that he was known for. Edison lived in New York City, was politically connected, and loved to put on a good show. He leveraged his fame, his name, and his face to his advantage in business. Direct current power became popular, and Thomas Edison became a leader in the field.
I mean, Edison had the market and built the first power station in New York for transmissional lighting. J.P. Morgan actually had the first house that was lit.
In contrast, George Westinghouse did not even like to be photographed. Yet the limitations of DC power were very clear to him. He felt that electric power should be generated in one place and be transmitted to users far away. In 1885, George Westinghouse became interested in the inventions of European inventors Galliard and Gibbs, relating to the use of single-phase alternating currents and distribution with transformers.
George Westinghouse was the first to recognize that you could use a transformer in a large system. With alternating current, you can transform the voltage up to a high voltage, low current, and send it hundreds and thousands of miles at the high voltage and step it back down to the low voltage where you use it. It was the key to the entire system.
He purchased the American rights to their patent and threw himself into the study and design of a new kind of transformer. It was said that he recalled his experiences in the gas industry with the reducing valve that allowed high-pressure gas from the well to be transported over a great distance and then delivered at low pressure at the point of use. The transformer was his reducing valve for electricity.
That's exactly what he was doing with gas transmission, because voltage is pressure. It's the exact same term in electricity as it is in hydraulics and gas fluid. He could step up the voltage to transmit it at a faster speed, and then when he got to the houses, he could step it back down again.
Those who watched him work were stunned at his capacity to do extraordinary things quickly. Through long evenings, he would work in his private railroad car and in his house, designing, sketching, and dictating. When at home, he often worked on his billiard table. It was said he never had a pencil, but just borrowed one from the nearest man. He never returned any of the pencils, and nobody knows what happened to them. One writer said that his trail through the world was blazed with other men's pencils.
The answer might surprise you, but do you know how much time it took?
So now you saw how the first system worked. Now we'll see how we moved on from there. As I told you, it was the invention of transformer which changed the entire power system field. The main principle on which transformers operate, we all know, is electromagnetic induction, which was discovered by Michael Faraday in 1831. Little did Faraday know that his discovery of electromagnetic induction would be the foundation of every single electrical product which evolved later on. Transformers, electric generators, electric motors, all of them, they use the concept of induction. So he performed a very simple experiment. He had two coils and he observed the induction between the two coils. I think in physics, high school physics, we would have all seen Faraday's famous experiment. So what he did was he had two coils separated by a distance, and when one coil was energized, that means when one coil had current flowing through it, a galvanometer connected to the other coil deflected. So he was perplexed. There is no electrical connection between the two coils, and how did a current changing in one coil deflect a galvanometer connected to the other coil, which is placed at a distance and which is not even electrically coupled? So that led to the beautiful discovery of electromagnetic induction. However, Faraday did not invent the first transformer, right? So there were three people, Blethy, Derry and Zipernowsky, who first designed and used the transformer in both commercial and experimental systems. Later on, we had, under the leadership of William Stanley and his team, Ferranti and Gorlard, they perfected the design of the transformer. And in 1886, funded by Westinghouse, Stanley demonstrated the first AC power systems in Great Barrington. So you see now, this transformer is based on the principle of electromagnetic induction. So we all know what is a transformer. So you primarily have two coils, a primary coil and a secondary coil. So when you pass current through the primary coil, a voltage is induced in the secondary coil. Okay? And if you connect a load to the secondary coil, this voltage can drive a current. So this is the simple concept of a transformer. So you would have all studied it under the course in transformers. So what did this do? What did this transformer essentially do to revolutionize the concept of the power system? So you all know that transformer enables stepping up and stepping down of voltages. How do you do it? Very simple, you just have to change the number of turns in the primary and secondary. So V1 by V2, where V1 is the primary voltage and V2 is the secondary voltage, is equal to N1 by N2. N1 is the number of turns on the primary and N2 is number of turns on the secondary, right? So by just changing and playing around with the number of turns, you can have different voltage levels stepping up and stepping down. So this was one of the first inventions in favor of AC. I can't do it in DC because electromagnetic induction says that to induce a voltage you need a changing magnetic field. I need a changing magnetic field. So you all know the voltage induced, you would have studied the laws of electromagnetic induction. The voltage induced is proportional to the number of turns and the rate of change of flux. So E is proportional to N d phi by dt. So if I use DC, phi is a constant. So except in the instant where you just apply the DC voltage with a switch, the flux is a constant and therefore cannot induce voltage. So transformers are the first invention which led to people thinking of using AC for transmission instead of DC as suggested by Edison. The second great invention was that of the induction motor. So the induction motor completely replaced the DC motor. What is the issue with DC motors? So the problem with both DC generators and motors is commutation. Okay? So this commutation process makes DC machines expensive and also very difficult to maintain. So now we had two products in the market. One is the transformer, which enabled change in the voltage levels, and other is the induction motor, which replaced the DC motors. So, these two together paved the way for a natural choice for AC. Okay. Now, you can just see here a simple coil here. This is the simple electromagnetic induction, okay, the experiment which Faraday did. So, here you have a battery and you have a switch, you can see that, and there is a coil, second coil, and there is no electrical connection between coil 1 and 2, and there is a galvanometer connected here. So, every time this switch was turned on and off, this galvanometer deflected, the galvanometer deflected. So, this is what led to the discovery of electromagnetic induction. It is not an invention, it was already there in nature, and Faraday happened to discover that. And now this is the first transformer available at the Berkshire Museum. So, I have given the source here, the image is taken from the source quoted. Now, the first transformer, how did it operate? We will just see a few interesting things because you are all used to modern transformers. So, this is the first one. The frequency was 133 and 1/3 cycles, an odd number, right, 133.33 hertz. Okay. So, if you just calculate in one cycle, you have two alterations, right. So, it goes from positive and then negative. So, if you just calculate per minute for 133 1/3 hertz, you will get 16,000 alternations per minute. That means 16,000 times positive, negative, positive, negative. So, it goes through the 0 16,000 times. So, it is historically called as the 16,000 alternations per minute. So, this was the first transformer design. I am giving you this because I want you to understand the history of evolution and how beautifully in a short span of 100 years the entire power system has changed from a very, very primitive level to a very, very sophisticated modern power system. And it was a single phase AC system. It was a single phase AC system, and the transmission length was around 4,000 feet. So, roughly around, slightly more than a kilometer, and it was built by Westinghouse and backed by research on transformers by Siemens at that time. And what they used was Siemens alternators, transformers from Westinghouse, and Edison incandescent bulbs. So, even then the Edison incandescent bulbs, we all know till very recently were very popularly used. This is what the system used. And the maximum power output was 25 horsepower, and again it was powered by a Siemens alternator. The generator used was a Siemens alternator, and the voltage was 500 volts, and it was reduced to 100 volts using a transformer, and this was supplied to all the homes. Okay. So, you can check out on this reference to get more details if you are interested. It is a very interesting article. So, this is the first motor designed, induction motor, and a very small motor. The very small motor, hardly 1/4 HP, 0.25 HP. Today you have motors, I do not know if you even can imagine, around 7,000, 10,000 HP motors are available. Okay, you have 500 megawatt generators, huge machines. So, the first one was hardly 0.25 HP and ran at 1800 RPM. So, I suggest all of you kindly go to this source and read more. It is always very good for engineers to know how a system has evolved, so that from your starting point you can think of ways to improve it and go forward, and you will get an idea about the great contributions throughout the history and how you can take it forward. That is why I always make it a point to put some historical points and milestones into the lectures. Now, The induction motor was a total replacement to DC motors, and again, as I said, this made an AC system a natural choice over DC. AC voltage can be converted to different voltage levels with just a transformer, making it easier to transport across great distances. So, we saw in the previous video the first DC system of Edison. So, the first AC transmission system was in 1890. It was single phase and commissioned and operated in the United States. So, electric power was generated using two 300 HP water wheel turbines at 4 kilovolts. Okay. This single phase system fed power over 14 miles. So, you see a lot of improvement from 1.5 kilometers, they could go up to 14 miles from Oregon City to Portland. So, this was the first milestone, and it was a much bigger transmission system than what was available earlier. So, you can just see here, this is what it looked like, and these are the water wheel turbines here, and this is the first AC system. Now, for the same system, that is a 14-mile system, and for the power generated, if a DC system was used as was earlier, it would have incurred heavy losses and would have had a very large voltage drop. So, what do you mean by a voltage drop? You all know that. So, when current passes through a conductor, there is a voltage drop in the conductor, right. So, this voltage drop is equal to IR if the current is DC and IZ if the current is AC. So, Z you know is R plus JX. So, both the resistance and reactance of the conductor will affect the voltage drop, right. In 1888, Tesla developed many more polyphase AC systems, and he had patents of motors, AC generators, transformers and transmission lines. Ultimately, Westinghouse purchased all these patents from Tesla, and they started developing AC transmission systems. So, the earlier AC transmission systems were all by Westinghouse. For some time, both AC and DC systems were existing in parallel, but due to the limitations of DC systems, as we had seen, AC systems reached far greater heights. They were scaled up, and slowly DC started fading away until they made a re-entry. After the power electronic technology matured and came again back into the power system as HVDC transmission systems. Now, it is very interesting. During this debate, Edison recommended DC and Westinghouse strongly advocated AC. After all, Westinghouse held all the patents for AC products. Okay. So, this is a very interesting video on the electricity feud between Westinghouse and Thomas Edison. This video is available on YouTube, and I place on record our acknowledgement to YouTube for making it available to the public. Please see this video. It is very interesting for you to know how there was an intense debate on whether to continue with DC systems or to go in for AC systems.
The development of electricity was like the rapid development of the automobile, computers, or the internet. Everyone could see that it was useful and amazing, but nobody knew quite how to utilize it or what the standards would be. It could be said that Thomas Edison created the idea of a centrally located power station. The only problem was that the direct current power he was using did not transmit very far.
You could only transmit direct current a few thousand yards from a Edison generating station.
It was quite obvious to George Westinghouse that direct current was never going to be a national model. It's just a local model.
That meant that in order to power a city, he would need power stations every mile or so that were small and practically in their customers' backyards. The development of electricity was like the rapid development of the automobile, computers, or the internet. Everyone could see that it was useful and amazing, but nobody knew quite how to utilize it or what the standards would be. It could be said that Thomas Edison created the idea of a centrally located power station. The only problem was that the direct current power he was using did not transmit very far.
You could only transmit direct current a few thousand yards from a Edison generating station.
It was quite obvious to George Westinghouse that direct current was never going to be a national model. It's just a local model.
That meant that in order to power a city, he would need power stations every mile or so that were small and practically in their customers' backyards. These facts did not stop Edison from promoting DC power with the theatrics and flair that he was known for. Edison lived in New York City, was politically connected, and loved to put on a good show. He leveraged his fame, his name, and his face to his advantage in business. Direct current power became popular, and Thomas Edison became a leader in the field.
I mean, Edison had the market and built the first power station in New York for transmission lighting. J.P. Morgan actually had the first house that was lit.
In contrast, George Westinghouse did not even like to be photographed. Yet the limitations of DC power were very clear to him. He felt that electric power should be generated in one place and be transmitted to users far away. In 1885, George Westinghouse became interested in the inventions of European inventors Galliard and Gibbs, relating to the use of single-phase alternating currents and distribution with transformers.
George Westinghouse was the first to recognize that you could use a transformer in a large system. With alternating current, you can transform the voltage up to a high voltage, low current, and send it hundreds and thousands of miles at the high voltage and step it back down to the low voltage where you use it. It was the key to the entire system.
He purchased the American rights to their patent and threw himself into the study and design of a new kind of transformer. It was said that he recalled his experiences in the gas industry with the reducing valve that allowed high-pressure gas from the well to be transported over a great distance and then delivered at low pressure at the point of use. The transformer was his reducing valve for electricity.
That's exactly what he was doing with gas transmission, because voltage is pressure. It's the exact same term in electricity as it is in hydraulics and gas fluid. He could step up the voltage to transmit it at a faster speed, and then when he got to the houses, he could step it back down again.
Those who watched him work were stunned at his capacity to do extraordinary things quickly. Through long evenings, he would work in his private railroad car and in his house, designing, sketching, and dictating. When at home, he often worked on his billiard table. It was said he never had a pencil, but just borrowed one from the nearest man. He never returned any of the pencils, and nobody knows what happened to them. One writer said that his trail through the world was blazed with other men's pencils.
Now that you have watched the video, let us see what were the main reasons for AC to flourish and reach greater heights, and why AC could reach longer transmission lines. One is the possibility to increase the voltage levels. Now, it must immediately strike you, why should a higher voltage level be needed at all? Very simple. We all know whether it is AC or DC, the power is proportional to the voltage and current, product of voltage and current. If it is DC, it is simply the voltage and current. If it is AC, it is the RMS value of voltage and current, right? Now, for a fixed power, the power is determined by the consumer. So, every product we use, every load, we say it's a load, requires a certain power. So, I have no control on it. It is designed for that and it requires that. So, for a given power, whether it is AC or DC, if the voltage is higher, the current will be lower, the current drawn will be lower, obviously, because P is proportional to the product of voltage and current. So, what is the conclusion? At higher voltages, the same power can be transmitted with lesser current, right? Beautiful. What does lesser current mean? Lesser current means lesser losses, I squared R loss. So, lesser losses and also lesser voltage drops. The voltage drop is I into Z. So, if I reduces, the voltage drop will also reduce. So, now you can see why I kept harping about higher voltages, higher voltages. So, with DC, I do not have a way of stepping up the voltage. Whatever voltage I generate, I have to use the same voltage. That is the reason why DC systems resulted in heavy losses. Whereas in AC, I have the transformer, I can step up at very high levels and transmit the power at the high level. Okay? So, once I transmit power at higher voltages, automatically my current flowing through the lines will reduce, my losses will reduce, my voltage drop will reduce, my efficiency will increase, and there are so many advantages. So, this is one single reason why AC systems became very, very popular. And in terms of generators, I told you by this time there was a lot of work done on invention of AC motors, single phase, polyphase, AC generators, and these were much cheaper than the DC counterparts. You do not have the problem of commutation, okay? Brushes, wearing out of brushes and so on. So, the AC generator technology was another driving force for AC transmission systems to replace DC. And when it comes to motors, the induction motors are very rugged and can be produced over a wide range of powers. Therefore, these three reasons pushed the entire globe into replacing DC systems with AC systems. So, AC systems started becoming more popular. Now, when you think of a transformer, you would have studied in transformers, there is a lot of design involved, right? So, I need to design the coils, I need to design the core, we need to design the insulators, the cooling systems and so on. Well, I have a strategy to transform from one voltage level to other level. This is theoretical. So, V1 by V2 equal to N1 by N2 is a mathematical formula, but I can't just have any voltage I want. I can't transform, say for example, 10 volts to 10,000 kilovolts. I can't do it. Why? There are so many limitations, right? As I told you, the design of the transformer comes into picture. Therefore, as the transformer material technology, different materials came into the market, different types of core, laminations, different types of cooling systems. So, all these over a period led to better and better transformers. So, slowly if you look at the history, the voltage levels of transmission kept becoming higher and higher. Okay? So, with advancement of insulating materials, transmission voltage levels started increasing. So, in 1922, it had reached a level of around 165 kilovolts, whereas in 1990s, it was around 1100 kV, and today people are experimenting with higher voltages. Now, as I told you, though you have the technology, you just cannot go up to very high voltages because there will be a lot of electromagnetic fields around the transmission lines, and they will definitely affect the environment around. So, we still have a limitation on the voltage levels. We just cannot go on increasing it to higher and higher levels. Okay. So, in 1893, the first three-phase AC transmission system was commissioned with a voltage of around 2.3 kV. So, it took a couple of years. Why? Because I needed a three-phase alternator, a matured, reasonably good efficiency three-phase alternator, and we needed a three-phase induction motor. So, all this took some time, and in 1893 we had the first three-phase AC transmission system with around 2.3 kilovolts. Now, the voltage levels are different for different countries, and in a country it is standardized. So, in India, if you take our domestic supply, it is 230 volts single phase, and 230 volts is the RMS value. So, I want you all to keep in mind that in AC system, whenever we talk of the voltage, we are talking of the RMS value. We are talking of the RMS value. So, in a particular country, the voltage level is standardized so that you can have interconnections of products. So, throughout the country, every single electrical product designed should operate at the same voltage and the same frequency, the standard voltage and the standard frequency. So, if my equipment requires a different voltage, then at the consumer end I again have to use a transformer and step down my what we call as the utility voltage. Utility voltage is the voltage you get from the utility. So, I have to step down the utility voltage to my requirements if I want a lower voltage from what I am getting at the utility level. So, whenever you travel and you want to take a product, let us say you travel from India to say Australia or UK or US, and you want to take an electrical product like a mixer or a coffee maker, you have to make sure that you have matching electrical parameters, that is the voltage and frequencies. Now, let us see what was the next issue. So, you saw that the first system had 133.33 hertz. Again, as it evolves, that was an experiment, the first system. As the technology evolves, we have to standardize, because standardization always improves interoperability. So, people started wondering what is the best frequency to have for generation and transmission and distribution. So, if the frequency is too low, then for a given power, your generators and motors, the size will be very large. If it is too high, losses will be more. You have seen the iron losses, they are all proportional to frequency. They all depend on the frequency. So, if I operate the system at high frequencies, I will have to compromise on the efficiency, right? That will become very costly. And if I operate at very low frequencies, the size of the equipment required will be very large. That again becomes expensive because I need more material. So, now 50 hertz and 60 hertz are standardized. So, USA, Canada operates at 60 hertz, and India and other Asian countries and Europe, we all operate at 50 hertz. This is neither too low nor too high. So, now you can just see a very simple system here, a very simple system I have drawn. So, what happens? I generate at around 11 to 33 kV normally. So, you have 11 kV generators, 22 kV generators, 33 kV generators at the main generating stations. Okay. So, we saw that I need to step up the voltages, because higher voltage means better efficiency. So, the transmission levels I have just shown here as an illustration, 220 kV to 400 kV, it can be higher. I told you we have gone up to higher voltages. But throughout the country you won't be running at around 1100 kV, it is not possible because there is a lot of life around. Okay, so you can't, we don't operate at such high voltages. So, the general range of transmission voltage is between 220 kV to 400 kV. So, here a step up occurs. So, between the generator and the transmission line, I need a transformer. And what should this transformer do? It should step up the voltage, the generated voltage to the transmission levels. Now, so it is transmitted over longer distances. Then we have substations where you can bring down this voltage to say between 33 to 66 kV. 33 to 66 kV. Okay. So, I bring it down again using transformers. Now, there may be many industries who will tap the voltage here. You can see here large customers, consumers are all industries. The industries will require at a higher voltage. Okay. Next, what happens? You come to the distribution level, right? You have a primary distribution between 11 to 33 kV. Again, large consumers can tap at that voltage. They can take the power at that voltage. And then finally, we have a secondary distribution where you can see small consumers, people like you and me, normal, domestic, okay, and maybe a farm, a villa. So, we need at lower voltages. Our gadgets are all at lower voltages. So, if you see in India, as I told you, it is 230 volts, and if it is 3-phase, it will be between 415 to 440 volts. So, this is a very simple picture of the generation, transmission and distribution system, a very simple picture. So, just keep in mind, I have a generator, I step up the voltage, okay, then I step down to some level which the major industries need, then I step it down further where the smaller industries can take, and then I bring it down to the lowest level of distribution where ordinary consumers will tap the power. Clear? Now, you should bear in mind that it is not just this, just a generator, transmitter, transmission line and distribution lines. No, there is so much of protection which goes into the system, right? Faults can occur, lightnings can strike, some tree may hit a conductor, there might be an electrocution somewhere, power will be distributed, heavy rain, snow. So, there is a huge aspect of power system which is called as the protection of the system, which is a course in itself, and you will be doing it maybe in your higher semester. So, please bear in mind that at every place you have the protection system in place to protect the people and animals around. Okay? So, this is just a recap of what the diagram says. The electric power is generated at a voltage of 11 to 33 kV and stepped up to transmission levels. The transmission capacity of a line is proportional to the square of its voltage. So, when you talk of transmission capacity, you are talking of the power. So, we know power is proportional to V squared. Power is proportional to V squared. So, the capacity is proportional to the square of the voltage. So, the voltages are expected to rise to around 1200 kV more lines in the near future. And India, we have a lot of 765 kV lines also. Now, I told you DC made a re-entry somewhere in the second half of 20th century, 1960s, 70s, and DC made a re-entry. What is the reason? So, after Edison fought for DC and people said, no, we are not going to have DC, we are going in for AC. Again, after almost 7 to 8 decades, why did DC make a comeback? Because power electronic technology matured. So, we had devices, the thyristors, the IGBTs and so on, which facilitated a conversion from AC to DC and DC to AC. Okay? And then people started seeing whether DC systems are better for transmission over long distance. Now, by then, please remember, in this 7 decades, 70 years, all our products were AC, right? Motors, lamps, everything, they were all working on AC. We didn't still have computers and mobiles which needed DC for charging, no. So, the loads were all AC. So, if I transmit DC, generators were also AC. At the generating end, I have to, convert the AC to DC, transmit DC, and again at the receiving end, I have to step down the DC, change it from DC to AC because the loads need AC. So, DC transmission started coming into picture. So, in the next session, maybe we will see why DC transmission was preferred. because they found that more than 600 kV AC transmission systems were no longer economical. See, all of you from basic circuit theory, you should know that the inductance doesn't offer any reactance to DC, because the inductive reactance we all know is L omega, and omega is equal to 0 for DC. So, the X component in your Z doesn't affect the voltage drop. So, the voltage drop in DC is simply IR, whereas in AC it will be IZ. Okay. Therefore, the resistance of the conductors are always low as compared to the inductance. Hence, people thought, they found that at higher distances, DC transmission is more viable and cheaper than AC. And that was again the rebirth of DC in the form of HVDC transmission systems. And the next revolution came maybe just a decade ago with the solar power. So, that solar photovoltaic power generation, the technology matured. We had very good materials and very good technology to generate power using the sun's energy, which is very cheap. But the one thing is, the voltage generated is DC and low voltage. So, with this again low voltage DC started coming into the market. But now here we have a paradox. For 100 years we have developed AC systems, all our products depending on AC, and your mobile, your laptop, everything which requires DC, what I do? You put a charger, you put a charger or an adapter. It will change the, they'll step down the voltage and then rectify it and charge your battery with DC. So, with electronic devices, we had a lot of equipment and devices which required DC, but our main system was AC. So, we were actually converting again to AC to DC at the low voltages. And now with solar power, I got a beautiful way of generating DC voltage, and people started thinking, hey, let me start using DC. So, today again there is a lot of work going on in the area of LVDC, low voltage DC. We have so many products which require DC. All your electronic gadgets need DC. LEDs work beautifully, lighting. LEDs work beautifully with DC. And then we have very good motors now, the motor technology which work with DC. And so, now again the interest in DC is coming up, okay, for use at the consumer level. It is cost effective if DC transmission is employed to transmit bulk power, and widely used all over the world. Today DC transmission lines are used everywhere, USA, China, a lot of places in Europe. In India also we have plenty of DC lines. So, this is an idea of what voltage levels we use in India normally. So, if your nominal voltage is 765, so please remember, I cannot get exactly 765 volts because the load keeps changing. When the load changes in the system, what happens? The current changes, right? So, what exactly is happening? You can just visualize quickly. I have a generated voltage, I step it up, right? And the power is transmitted over a long distance in the transmission line. So, when I come to the receiving end, I won't have the same voltage because there will be some voltage drop in the line. We saw the line drop is equal to I into Z. So, the receiving end voltage will normally be less than the sending end voltage. There is a drop. So, if I have a 765 kV line, I won't be operating exactly at you can't, not I won't, I can't operate at exactly 765 kV. For the simple reason, the load on the power system is dynamic. Possibly this course is one of your first courses in power system, and you will see that it's a very complex system to operate. It's a very, very dynamic system, very dynamic system. Okay, so your generators, if you take a AC system, the generators are rotating, and then the loads, all the motors, majority of the industrial loads, the motors, they're all rotating systems, and the load is never continuous. The load continuously changes, rapid change, though it has a pattern. So what in any country they do is, once you have a specified voltage, then a small amount of deviation is permitted. Okay? That is the standard prescribed by every country. Obviously, if I promise to give you 230 volts, I can't give you 110 volts. Your equipment will get damaged, right? So I won't be, having a very wide variation. I'll have a margin. You will see these aspects again when we come to the module on power quality. What's the quality we get, right? So if you have 765, then you can vary from around 800 to 728 kV. And so for 400 kV lines, from 420 to 380, and so on. And for 33 kV lines, you can go from around 36 to 30. Okay. So this is prescribed in every country. What is the deviation permitted and the operators of the system. So you see, we have different operators, different people operating the system have to ensure that this is adhered to. Otherwise, we cannot operate the system. We can't operate the system. So this is about transmission. So what are the key features in transmission? Only one thing, mainly one thing which we saw, that is stepping up of the voltage. Stepping up of the voltage and different voltage levels. And we saw that 600 kV is somehow like a cutoff point, helping you to decide between AC and DC. Helping you to decide between AC and DC. So the next is the distribution system, which we will see in the next session.